Welcome to Paris class number 129, and today we're talking about an interesting idea when it comes to propellers, and not just any propellers, but propellers for water. So when you think about a propeller that goes into water, you think, okay, you just put it into the water and you rotate it and you'll generate thrust. But that's not the only way that you can use regular propellers. And to look into this idea, we're going to be looking at a paper called Experimental Evaluation of the Effects of Positioning and Operating Parameters on the Performance of a Surface Piercing Propeller. And that last bit is the important bit, surface piercing propeller. So if the propeller is piercing the surface, then obviously the entire propeller is not inside the water. It's not engulfed in the water. And that's exactly what's happening here. The propeller is a little bit above the water, so only part of the propeller goes into the water. So that might seem a little bit strange. I should also mention that this paper you can find in the link in the description is open access. So you might find it a little bit strange to put the propeller only a little bit into the water. But why would we do such a thing? Well, there are a couple reasons why doing it this way is better than submerging the entire thing. So in figure 1, we can see here, this propeller is in the water only partially. And for those of you who are just listening to this, you can see this video on Spotify and or YouTube. And on our YouTube channel, you can also find a few goodies as well for you. So let's move on. What are some benefits to this type of propeller? Well, the first one is that when you have a fully submerged propeller, they're not good at high speeds for two reasons. The first one is cavitation occurs. So what is cavitation? Cavitation is when you have, for example, a propeller and it's moving very quickly through the water. You will get low pressure on certain edges and certain faces. That's how the propeller works. You have high pressure on one side and low pressure on the other. That's how force gets driven or force is created. So that low pressure can result in the water vaporizing. So you get such a low pressure that the water vaporizes. And you get effectively like these tiny little pockets of vapor. They look like air bubbles, but they're vapor, these little tiny pockets. And there's such low pressure that the surrounding pressure of the water makes them collapse very violently. And they collapse so quickly that often they can produce shock waves. And these shock waves will then impact the propeller and or the boat around wherever these little bubbles are forming. And they can actually take dents out of like solid material, like they can take dents out of hardened steel. And to look at this, you can look at like old boats that are from the maybe 80s, 90s that have been having 20, 30 years of operation. And you can look at these propellers and you'll see these divots being taken out of the metal. That's from repeated use from this cavitation. That's how detrimental they can be. And they usually reduce the efficiency and thrust of the propeller. That's one reason why fully submerging a propeller in the water is not good. The second reason is that the general propeller's efficiency drops because there is more drag on the supporting structure. So if you put the entire propeller into the water, you have to have something holding this propeller, obviously, so the shaft, and often you have housing around the propeller. And putting this propeller entirely in the water usually results in the housing plus this shaft that comes out of the propeller to be immersed as well. Well, that's more surface area for the water to go over, which then results in increased skin friction drag. What's more, these housings in that, they're usually not hydrodynamic or streamlined, so they then result in greater pressure drag as well. So by partially immersing the propeller, you can then put the propeller's shaft and housing outside of the water. And that means that it's now interacting with the air, which is obviously far less draggy than water. The density of air is 1,000th of that of water. So you're not going to develop nearly as much drag. So that's far more efficient. Those are two reasons why you'd want to partially submerge the propeller. Now, I mentioned earlier that if you partially submerge the propeller, you'll get a reduced cavitation. So why is that? I should discuss this a little bit more. So partially submerging a propeller results in the backside of each blade to be exposed to the air enough to prevent cavitation from forming. So the air can then like meet these little bubbles that form, and now you no longer have such a massive difference in pressure inside the bubble compared to outside of the bubble, because the surrounding medium is now air, which is at a lower pressure compared to water, and that will then result in the bubble not collapsing in such a violent way. That's how you can prevent this cavitation from forming and from negatively impacting the propeller. So for surface piercing propellers, or SPPs as they are known, only part of the propellers enter the water and none of the surrounding parts, as I mentioned. So this results also in the top speed increasing as well as the fuel consumption decreasing. This also allows the propellers to be bigger because you can place the propeller further away from the back of the boat, so you have more geometry to work with, and that means you can develop more thrust potentially. So with all these positives, surface piercing propellers have one major problem that arises and which limits its use. And that is they're hard to design. The flow physics is complicated because you have the water, plus now this propeller going in, plus now the air. So this is a multi-phase flow, and a major difficulty of this is not only just trying to figure out how these different geometrical parameters like the pitch and the yaw and whatever affect the propeller's performance, but also how to test these things. So because we have a multi-phase flow, trying to scale the test to like a water tunnel kind of situation is quite difficult. Let me explain why. So in pretty much all fluid mechanics, we usually use wind tunnels and water channels, etc., to test things, but we scale things down. So we don't test an entire airplane inside in a wind tunnel, and we don't test an entire boat inside a water channel. We scale these things down. The question then becomes, well, how do we scale it? Because we usually think about the Reynolds number, where if we have a big wing, for example, that we want to test in a wind tunnel, if we have a Reynolds number of 1 million in real life, we just match that Reynolds number in a wind tunnel, and that's fine. But if we were to do the same thing in a water channel, so let's say we have this propeller operating at a Reynolds number of 1 million, and we match the Reynolds numbers, we'll get dissimilarities between other things. For example, the Froude number, which is an important ratio which determines how the water is acting based on the water speed and the gravitational forces and the length scales. We'll get into that in a second. So these similarity laws break down because you can get one non-dimensional coefficient to be similar, but the other non-dimensional coefficient to be not similar. So which one do you go for? And that's a major problem. So how do we test this thing? And that's partly what this paper is going to be looking at. So we're going to divide this into two podcasts. This first podcast, we're going to go through all this theory and the ideas behind a surface piercing propeller and propellers in general. And the reason why we're going to do this in the first podcast is because it's very intense in terms of the new ideas that we will be presenting. Then the second podcast will be going into the results. I don't think we can do both of them in one podcast because I think your head's going to be spinning with all the different terminologies that we're going to be throwing around. So I think one podcast should be dedicated to those terminologies and what they mean and general ideas. And then the second podcast will be the details of the results. And we'll recap the terminology in the second podcast just to refresh your mind as well. So let's move on. So for example, a researcher called Shields demonstrated that the hydrodynamic behavior of a supercavitating propeller, so I should mention supercavitating propeller, not subcavitating. We'll mention what the difference is at the moment in a second. So a supercavitating propeller with a Froude number above 4 is independent of this number, while lower Froude numbers increase the force on the blade. So in other words, this is what I mean here, where when you have the similarity laws, let's say you want to match Reynolds numbers, and then you go, okay, fine, the Froude number is going to be a little bit different. How does that affect the propeller's performance? Well, they found here, if the Froude number is above 4, then the force on the blades aren't really affected too much. If it's below 4, then they are affected significantly by changing the Froude number. So then we would say, okay, we'll match the Froude numbers, but then the Reynolds numbers are different because the geometries are different and the velocities are different, and then that will result in different flow attachments and separations over the propeller. That's a major problem. Now, one thing I mentioned was supercavitating propellers. What is that? So this is another term. So I mentioned cavitation and what that was. So what is supercavitating? Supercavitating is where you actually use these cavities for your benefit. And what you do here is you have this propeller, and around the edges, you have cavities forming, these bubbles forming. And the benefit of these bubbles is that they are very low density compared to the water. So if you have part of the blade, each and every blade subjected to these cavities, part of the blade surface area will now be in this lower density medium. What this does is it reduces the drag on the propeller. And that means you can get a more efficient propeller by utilizing these cavities. That's what a supercavitating propeller is. It's one that is utilizing these cavities for its benefit. Whereas a subcavitating propeller is one where these cavities do form, this cavitation does form, but that is detrimental to the propeller's performance because it hasn't been designed to operate in such a situation. That's the difference between supercavitating and subcavitating. So In addition to determining experimental similarity laws, so whether we want to keep the Froude numbers or the Reynolds numbers constant or whatever, it is also important to know how the propeller's geometry affects its performance too. That would be a good idea, considering that you can change everything about a propeller. You can change its pitch, its blade profile, its size, its speed that it rotates at, its tilt angle, everything. So this current study investigates a custom four-blade surface-piercing propeller with a special blade section. It is designed to reach speeds of up to 40 knots and has a diameter of 60 centimeters. So 60 centimeters is a really big propeller for a regular boat, and the reason why they can get away with such a thing is because it is surface-piercing. It's not completely submerged, which means that you can put it further away from the boat, and you don't have, first of all, the effects of the propeller acting on the boat, nor the geometry of the boat constricting the propeller's geometry. So that's quite nice. They investigated the effect of the Froude number on the hydrodynamic coefficients, as well as the effect of the immersion ratio, so how much the blades are immersed, and also the yaw angles. The similarity numbers that they considered were the advance ratio, the thrust coefficient, the torque coefficient, and the efficiency. So the advance ratio is how much the propeller is advancing with every spin if the water didn't get out of the way. So for example, if you were to put this propeller in a very soft medium, for example, like a really hard goo perhaps, or cheese or something, and you were to spin this propeller, how far would it go? The thrust coefficient and torque coefficient are exactly that. They're like how much thrust and torque are being produced. The efficiency is, again, what you'd expect, the efficiency of the propeller. So the hydrodynamic coefficients of the surface-piercing propellers depend on numerous parameters that can be divided into three general categories. The first category includes the position parameters. So let's see figure 1, for example, where we have the yaw angles, the tilt, the rotation, the number of the height into the water, and etc. And this relates to the position of the propeller from the freestream surface and the direction of the water flow, such as the inclination angle, the shaft yaw angle, and the tip immersion ratio. So the tip immersion ratio is how deep into the water this tip is compared to the entire diameter of the propeller. They also talk about the effects. The second category is composed of geometrical parameters related to the hub and blade geometries, such as the diameter, the pitch ratio, which is how far the blade will move in one rotation compared to the diameter of the blade number, so how many of these blades there are, and the expanded area ratio, and the distribution of the rake angle, skew angle, and blade section. Let's talk about the expanded area ratio, and for this I want to get paint up, I think. Okay, so the expanded area ratio is quite an interesting idea. So if you were to have a flat propeller, like if you look on like a cross section and it just looks like this and it spins around, then the expanded ratio is simply just the projected area of this blade. But if you have a curved blade like this, the expanded area ratio is when you straighten out the entire blade and then you see what the area of this expanded blade is. So that's obviously greater than just the projected area. And that is what the expanded area ratio is. So there are a bunch of terms that we can like characterize the propeller's geometry through. So these are two categories that the hydrodynamic coefficients of the surface-piercing propeller can be divided into. There's a third category as well. And this is it includes the operational parameters depending on the physics and characteristics of the water flow, such as the velocity, the ambient pressure, and the propeller's rotational speed, which are expressed as dimensionless numbers such as the Weber number, the Froude number, the Reynolds number, and the cavitation number. We're going to get to some of those in a second. I just covered the Froude number. We know the Reynolds number as well. If you don't know the Reynolds number, then check out on our YouTube channel one of our videos in the Aero Fundamentals. It's one of the very first ones on Reynolds number. And then the cavitation numbers we'll get into in a second. So interestingly, a researcher called Ding proceeded to define the Froude number above 3.5 as the independent range of propeller behavior for all areas. And similarly, another institute called the KSRI Institute found a similar sort of Froude number. So if you get the Froude number above 3.5, then the propeller kind of acts independent of these numbers. So like the thrust that it produces and efficiency, etc. They're not really affected when the Froude number goes above that. Below that, the Froude number does affect these parameters, and that's not the first time that we have looked at that. So let's move on to the cavitation number, which I mentioned before. The cavitation number for surface piercing propellers is defined through equation 6 and is also known as an effective parameter on the performance. So what is this? It is the static pressure divided by the vapor pressure divided by the dynamic pressure. What does this mean? So overall, it just tells you how close to cavitation you are. If you collapse this number, it means that you are now cavitating the flow, and the closer you are to that, the worse off your propeller is going to be acting because the more cavitation you have. So that's what the cavitation number is there. Now, what about the water tunnel and propeller model testing setup? We've covered some of the theory here and what the propeller does and these different numbers for similarity. How do they test their propeller? So they looked into a water channel, here they call it a water tunnel. It's in figure 2, we can see, we'll get into that in a second. The tunnel was composed of an open section, which was 250 millimeters by a 200 millimeter cross section, with a water velocity range of 2 meters to 10 meters per second. 10 meters per second in a water channel is freaking amazing. We'll get into in a second how they're able to do that, but 10 meters per second is really high in a water channel. The test section was an open area 1.5 meters long at atmospheric pressure, which hosts the propeller for test purposes, while the plexiglass walls of this section provided for photography for the propeller water. And that's normal, like you have clear sides so you can take pictures. Measurements of the loads exerted on the surface piercing propeller was conducted by a third module using a 4-component dynamometer system based on the coordinate system on the model and aligned with the propeller shaft. So the dynamometer system is just really a system that allows whatever you're testing to rotate while you measure forces such as torque and rotational speeds and efficiencies you can get out of that too. They're often used for cars. That's like a very common instrument, but they're using it here as well for this. The dynamometer comprised 2 component force balances to measure the lift and side forces, one component balance to measure the thrust of the propeller, and one S-type load cell to measure the propeller's reaction torque. So an S load cell is exactly that. It's like a load cell that's shaped in an S. Now it's a bit more blocky than a regular, like if you draw an S, just make it a bit blockier. And that's what an S shaped load cell looks like. And the reason why we use these is because they are very efficient, like they're very well suited to measuring compression and tension forces. There are lots of other load cells you can use, but the S load cells are good for that. So their water tunnel setup is shown in figure 2, and I wanted to discuss how they'll get able to get such high velocities. So this is a little bit different to a lot of water channel setups. A lot of water channel setups, you really have the pump that then leads into this area. It's like a wind tunnel effectively. You have this pump that's pumping water around. The water has to then go through the flow conditioning section where you have a honeycomb and mesh screens. These honeycombs and mesh screens do the exact same thing in water channels as they do in wind tunnels. That is, they straighten the flow and they get rid of the like big vortices by breaking them into small vortices, and they die out very quickly, which then reduces your turbulence intensity level. The flow then goes through a contraction. The contraction also helps condition the flow in terms of making it straighter and getting rid of some of the turbulence intensity level. It also accelerates the flow. And then you get into the test section, and then you have your model and you test it, and then the water goes around. Now, this does not have any of the flow conditioning set up as far as I can tell. It literally has a pump going into a tube, and that tube goes straight into the test section. And there's no honeycomb, there's no mesh screen, there's no contraction. So the honeycomb and mesh screens, they obviously slow the flow down, and you can only pump water through so quickly. The contraction as well, there is a limitation to that. So there's a trade-off between how much velocity you get out of the contraction versus how much you'll hold it up, as well as potential flow separations. They have no contraction here, so it's a very simple, like just throw the water down a tube and test it. That's how they're able to get such a high velocity in their water channel. So I wanted to clear that up before we move on. And a test setup here, they can see you have this entire load cell set up with a dynamometer connected to the propeller, and they stick the propeller into the water a certain amount, not the entire thing, so they can test how well the propeller performs with different immersion ratios. So according to table 2, which I have here, the error level of the estimated regression model for each sensor was less than 1%. So in other words, all the sensors that they have, so for example, the sensors to measure the lift, side force, torque, and thrust, they are like 99% or better in terms of the accuracy. That's pretty damn good. And finally, they have a propeller here, which shows the different forces. So you have the thrust in the way that you expect. It's like pushing out from the back of the propeller. The torque is in the way you'd expect it. It's anti-clockwise, is positive. You have the lift going up and the side force going to the side. One thing that I want to talk about with this propeller is if you look at the trailing edge, which are these ones here, the trailing edge curves so much. So it's really more like a scoop than a blade. The leading edge is quite straight and the chord is quite straight up until about the 50% chord mark. And then the propeller just curves really hardcore. And that's to increase the thrust of this propeller. And it's really just scooping the water through. And it's not really acting as you would a typical hydrofoil or airfoil. It's a bit more extreme than that. So if I'm not mistaken, that is, no, we still have, sorry, the model propeller and yes, experimental test conditions for the model propeller. So the model propeller has a diameter of 60 centimeters. It has a pitch ratio of 1.24. It's made of aluminium. The expanded area ratio is 0.58. So in other words, 58% of the area is taken up with this propeller's blade surface. And going to the model though, that I tested, the model diameter is 0.13 meters instead of 0.6. So it's less than 25% of the full scale model, or the full scale thing. So that's going to result in some dissimilarity in terms of its performance. Now they need to figure out which numbers they need to make similar to get reliable results. And that's what the next podcast will be covering. We can see here that we get to the end of this podcast and we'll go into the results in the next podcast. So that's the end of this podcast. If you liked it, make sure to like. And if you want to get more like this, make sure to subscribe or follow on Spotify. And if you want to learn more about this, you can check out the next podcast, which will come out in a few days' time, and our other podcasts, which we've done over 100 of now. And if you want to get better at CFD and or theory, check out our courses on Aerodynamics. Check out our courses in the link in the description. And if you want to make your experiments 2 to 4% more accurate, check out the MSU Hawk. The MSU Hawk is an instrument that we make, which actually measures the density of air. We've talked about density here a few times. And the good thing is that in water, the density of water sort of stays somewhat stable, I would say, compared to air at least. Air, it changes a lot. Like if you go into your wind tunnel in the morning and you test like anything, the density of air from that point to after lunch, when you come back and do some more testing, will change by 2 to 4%. That results in your results being inaccurate by that amount. And if you were to come back the next day and or the next week, month, season, whatever, the air density will change even more by up to 15% quite easily. And if you have a storm on a day, that's going to change it even more. So the density of air changes a lot more than what we give it credit for, and that results in a lot more inaccuracies in our data than what we'd like, and we don't even know it. So you need to measure the density of air there to get rid of those errors. What's more, if you were to use these results that you get from your wind tunnel to validate your CFD, obviously your CFD is going to be inaccurate now because your CFD was running at a certain density of air, which your experiments were not conducted at. And they were conducted at different densities anyway. So you need to have like this range occurring for your CFD if you want to get it right, or you can match the Reynolds numbers, which you need the density of air for anyway. So the MSU Hawk, which is the instrument we make to accurately measure the density of air, does this for you and gets rid of those errors for you. So then you can trust your results and you can find more trends. That's the instrument in the link in the description as well. Make sure to check that out. And I'll see you next podcast. Peace out, amigos.